Alright, non-resident training course, September 1998, Navy Electricity and Electronic Training Series, Module 2, Introduction to Alternate Current and Transformers, Navy Trial 14174, Distribution for Public Release, Distribution Unlimited. Alright, Table of Contents, Chapter Contents, a concept of the alternating current, induction, capacitance, inductive capacitive resistance, and inductive and capacitative resistance, and transformers. Appendix glossary, Greek alphabet, squares and square roots, US ACF formulas, trigonometry functions, trigonometry tables, and index. And then it goes through all the modules. Throughout the text of the course, we'll give you the technical manuals associated with the equipment that we'll be working on. You will find that below the notations and some of the paragraphs, the notations are used to emphasize the safety hazards if the care must be taken and observed. Warning, operation, procedure, practice, or a condition, etc., which may result in injury or death and not carefully observed or followed. Caution, any operation, procedure, practice, condition, etc., which may result in the damage to the equipment if not carefully observed or followed. And note, any operating procedure, practice, or condition which is essentially to emphasize and the instruction for the course. We'll skip that and move on to Chapter 1. Chapter 1, Concept of Alternating Current. Learning objective. The use upon completion of the chapter, you will be able to state the difference between AC and DC voltage and current, the advantage of the AC power transmission over DC power transmission. State the left-hand rule for conductor, relationship between the current and the magnetism. The state of the with which the AC power can be generated. State the relationship between the frequency, period of time, and wavelength. Compute peak-to-peak intensity, effectiveness of average value of the voltage and current. Compute the figures of the difference between the sin waves. Alright, concept of alternating current. All of our studies far has been direct current, that the current which does not change directly. However, that you saw in Module 1, we'll see later the module, the coil rotating the magnetic field that actually generates the current which regularly changes the direction. This is called alternating current, or AC, and DC. Alternating current is current which is continuously changes the amplitude with the reverse direction at the regular intervals. Learned previously with the direct current flow of the one direction that the amplitude of the current is determined by the number of electrons flowing with the past the point of the circuit in 1 second. An example of the comb of electrons moves points past the point of the wire in 1 second, and all of the electrons are moving in the same direction, amplitude with the direction of the current in wire 1 ampere. Similar to the half of the comb of the electric move in one direction past the point in the wire in a half a second. The reverse direction move at the same point with the opposite direction during the next half a second. The total is 1 comm, and the electric passes that point in 1 second. The amplitude of the alternating current is 1 amperes. Preceding comparison of the DC and AC is illustrated. Noticing that 1 white arrow plus 1 stripped arrow compromises 1 comb. Comparing DC and AC current flow in a wire. Alright, DC shows first half second. AC, the reference point, first half second. The second half would be the DC. And second half of the cycle AC would be backwards. 1 arrow equals half a comb. Define the direct current, define alternating current. Disadvantage of the DC compared with the AC. With the commercial use of electricity became the widespread with the United States, certain the disadvantage of the direct current of the home became apparent with the commercial direct current. Certain systems use of the voltage must be generated at a level the amplitude of the value required by the load to properly light a 240 volt lamp. For example, the DC generator must deliver 240 volts. If a 120 volt lamp is to be supplied power from a 240 volt generator resistor of another resistor or another 120 volt lamp must be placed in the series within the 120 volt lamp to drop extra 120 volts. When the resistor is used to reduce the voltage, the amount of power equal to the consumed by the lamp is wasted. Another disadvantage direct current system becomes evident with the direct current or the amperes from the generation station may be transported a long distance over wire to the consumer. When this happens, the large amount of power is lost due to the resistance or the ohms of the wire, but the power loss is equal to the ampere squared times the resistance. However, the loss of the greatly reduced the power is transmitted over the line's very high voltage level and low current level. There's not a practical solution for the power loss in the DC system, since the load would have then be operated with a dangerously high voltage. Because of the disadvantages related to transmitting using direct current, practically all modern commercial electrical power companies generate and distribute alternating current. Unlike direct voltage, alternating current can be stepped up and down amplitude by the device called the transformer. The transformer will be explained later in this model. Use the transformer power efficiency transmission electrical power over the long distance lines. At electrical power station, the transformer output power is a high voltage low current level. At the consumer end of the transmission line, the voltage is stepped down by the transformer. The value required by load due to the inherent advantages of the versatility. Alternating current has replaced the direct current in all but a few commercial power distribution systems. What are the disadvantages during direct current system with respect to the supply voltage disadvantage of the direct current due to the resistance of the transmission wires, and what kind of electrical wires used in modern power distribution systems? Voltage waveforms. You now know that there are two types of current voltage that is direct current and the voltage of the alternating current voltage. If the graph is constructed showing the amplitude of the DC voltage across the terminal of the battery with respect to time, it will appear in Figure 1.1 View A. The DC voltage shown with the constant amplitude. Some of the voltages can go through periodic changes in amplitude, like are shown with Figure 1.1b. The pattern will result with the changes in amplitude with respect to time implied with the graph paper known as a waveform. Figure 1.1 View B shows some of the common electrical waveforms. Other illustrated sin waves will be dealt with most often. Alright, View A shows the direct voltage 0 volts at one period of time, and also that is a square. Regular wave would be square, positive and negative volt. A sawtooth wave, or a sin wave, alternating voltage. For alternating voltage. The sin wave is illustrated in Figure 1.1b, View B, with the plot with the current, with the change of the amplitude, with the direction. Although several waves that produce the current, the method is based on the principle of electromagnetic induction is by far the easiest, most common method in use. The fundamental theories concerning the simple magnets, magnesium, will discuss in Module 1 how the magnetism can be used to produce electricity, with only briefly mentioned. The module will give the more depth in magnetism. The main points will be explained with how magnetism is affected with the electrical current. Conversely, with the electricity effect of the magnetism, the general subject area is most often covered with electromagnetism. And to properly understand electricity, you must first become familiar with the relationship between magnetism and electricity. For example, you must know an electric current always produces some form of magnetism. The most common use of producing electricity involves magnetism, and peculiar behavior of electricity under certain conditions is caused by magnetic influences. Right, magnetic fields. In 1819, Hans Christian Ørsted, a Danish physician, found the definite relationship exists between magnetism and electricity. They discovered the electrical current is always accompanied by certain magnetic effects that effectively obey definite laws. Magnetic field around current carrying conductor. If the compass is placed with the vicinity of the current carrying conductor, the compass needle will align with itself with the right angle of the conductor, indicating the presence of the magnetic force. You can also demonstrate the presence of the force using the arrangement illustrated in Figure 1.2. Both A and B with the figure current flow of the vertical conductor through the horizontal piece of the cardboard. You can determine the direction of the magnetic force produced with the current placed in the combs over the various points of the cardboard, noting that the compass needs deflection. Needle deflection. The direction of the magnetic force is to assume the direction in which the north pole of the compass points. Figure 1.2 shows the magnetic field around the current carrying conductors, the electromagnetic barrier, the fixed resistor switch, and the the piece of cardboard with the compass needle for the north and south. You also have electromagnetic field counterclockwise, going clockwise, and then electromagnetic field going counterclockwise, which the negative runs from a fixed resistor to a switch and over the plate, with reversing the still the north and south, but in a counterclockwise or reverse EMF. Figure 1.2, needle deflection shows the magnetic field exists with a circular form around the conductor. The current flows upward with the figure 1.2 with the direction of the field with a clockwise view of the top of the from the top. However, for the reverse polarity of the battery, so the current flows downward. The direction of the field is counterclockwise. The relationship between the direction of the magnetic line, the force of the round of the conductor, direction of the electrical current flow, if the conductor may be determined with the left-handed rule of the conductor. This graph, the conductor, if the left hand of the thumb extends into the direction of the electric flow current, and negative to positive, the fingers will point the direction of the magnetic line and force. Now apply the figure to 1.2, but know that the figures point the direction of the north pole of the compass point path of the place of the magnetic field surrounding the wire. An area generally is used in an electrical diagram to denote the direction of the current and length of the wire. See Figure 1.3a. When cross-section of the wire is shown with the in view of the arrows U, with the cross-section view of the conductor carrying the capacity, carrying current toward the observer, the illustrated Figure 1.3b. Note the direction of the current is indicated by a dot representing the head of the arrow, and a conductor that carries the current away from the Observer is illustrated in Figure 1.3c. Note that the direction of the current is indicated by a cross, representing with the tail of the arrow. Note that all the magnetic field around the current carrying the conductor is perpendicular to the conductor. The magnetic line with the force equal among all parts of the conductor. Figure show the magnetic fields are perpendicular. The magnetic fields are parallel to each other in the dot, and also this shows the current flowing from counterclockwise and across, the cross. When two adjacent parallel conductors carrying the current in the same direction, the magnetic line force combined with increase the strength of the field around the conductor shown in Figure 1.4a, with the two parallel conductors carrying the currents opposite direction shown in Figure 1.4b. Note that the field around one of the conductor opposite the direction field around the other conductor, resulting in line of force opposed to each other with the space between the wires deforming the field around each of the conductor. This means the two parallel adjacent conductors are carrying currents in the same direction, and the fields are about two conductors aid each other. The conversely, the two conductors are carrying currents in the opposite direction. Fields about the conductors repel each other. Figure 1 shows the magnetic field and two parallel conductors, current flowing in the same direction. And current flowing in the opposite directions repel. Alright. When placed in the vicinity of the current carrying conductor with the needle of the compass becomes the line with the angle of the conductor, which direction of the magnetic field around the vertical conductor, A with the current flow for the upward and B flow for the downward. Left-hand rule for the conductor is used for what purpose in the direction of the compass needle for the point with the compass plate for the magnetic field surrounding the wire. Two adjacent parallel wires carry current in the same direction. Magnetic field about the wire. One wire has the effect of the magnetic field with about one on the other conductor. When two adjacent parallel conductors carry the current with the opposite direction of the magnetic field about, one conductor has the effect of the magnetic field about with the conductor. Magnetic field of a coil. The Figure 1.3 illustrates the magnetic field around the current carrying the wire axis at all points along the wire. Figure 1.5 illustrates when straight wires wound around the core, the forms of the coil that magnify the field about the core, assumed with a different shape. Figure 1.5a, the actual partial cutaway view show with the construction of the simple view. Figure 1.5b show with the cross-sectional view of the same coil. Note that the two ends of the coil are identified as X and Y. So X is Y, and on the other end is Y. Show the core, the North Pole, and also show the positive and negative, positive and south that have the currents flowing. And one counterclock. When the occurs in passive of the coil with the magnetic field about each turn of the wire links with the field of the adjacent turn. Figure 1.4a, the combined influence of all the turns produced the two pole cells similar. Simple bar magnet. One end of the coil is North Pole, and the other end is South Pole. Polarity of electromagnetic coil. Figure 1 and 2 show the direction of the magnetic field around the straight wire depends on the direction of the current of the wire. The reversal of the current of the wire causes the reversal of the direction of the magnetic field to produce the follow with the reversal of the current coil. Use the reversal of the 2-point magnetic field about the coil. When the direction of the current coil is known, you can determine the magnetic polarity coil by using the left-hand rule for the coil, which is illustrated in Figure 1.6 as stated. It shows the left-hand rule for the coils. So basically, it's either in your left hand and you turn it around and you see that the directions change. Graph of the coil in the left hand with the fingers wrapped around the direction of the electron current flow. Then use your thumb and point it toward the North Pole of the coil. Strength of the electromagnet. The strength and intensity of the coil magnetic field depends on the number of the factors. The main one are listed below. We'll discuss again the number of the turns in the wire in the coil, the amount of the current flowing in the coil, the ratio of the coil length of the coil width, type of the material in the coil, losses in the electromagnetic field. When the current flows, the conductor atoms of the conductor all line up with the different direction produced the magnetic field. The direction of the current change with the direction of the atoms align with the also change with the magnetic field change with the direction reversal of all the atoms require the power expended with the power is loss of the loss of power in the form of the heat is called the hysteresis loss. The hysteresis loss is common in all AC equipment. However, it is also a case of view problem except for the motor generated with the transformer. When the device is discussed later in the module, hysteresis will be covered in more detail. What happens when the shape of the magnetic field exists around the straight conductor in a coil? What happens with the two magnetic coil will the current through the coil is reversed? What is the use of the determinant of the polarity of the coil? The directional electrical current flow with the coil is known. State the rule, the purpose of the described in question 14. Basic AC generator. The previous discussion you learned with the current carrying conductor produced the magnetic field itself. The module 1 unproduced the voltage EMF. Using the magnetism, using how the magnetic field to produce the EMF of the conductor. This conductor is placed in the magnetic field. Either field the conductor move the EMF is induced in the conductor. The effect is called electromagnetic induction. The cycle for the figure 1-7 and 1-8 to show the suspended loop of the wire being rotated and moved in clockwise direction magnetic field between the poles of the permanent magnet. For each of the explanation loop that is divided into dark half and the light half, notice that the A of the figure of the dark half is moving along the parallel lines of the force, constantly denoting the NO lines or of no lines of force, same as the true of the light half moving in the opposite direction. Since the conductor cutting no lines of force, the EMF, no EMF is induced. As the loop rotates toward the position shown in B, it cuts more and more lines of force per second, inducing every increase of the voltage because of the cutting more directly across the field line of force. At B, the conductor is shown with a completely 1/4 of the complete revolution, or at 90 degrees, or complete circle, because of the conductor is now cutting directly across the field of voltage, inducing the conductor's maximum of the voltage value with inducing the voltage various points during the rotation. A and B is plotted with the graph. The points are connected to the curve that appears as shown. Figure 1 shows as a simple alternating generator. The conductors move the parallel lines of the force EMF at the minimum, and rotation conductor and A, B, and C show that the conductors cutting the direction across the EMF at the maximum positive, and then as you notice, the fold is shaded of the angle, and then the rotation, the conductors cutting the direction across the field, the EMF at maximum negative. Alright, as the loop continues to rotate toward the position shown with the figure in blue and below C, it cuts fewer and fewer lines with force, inducing voltage degree for the peak of the value, but eventually the loop once again moves in the plane of the parallel magnetic field. No EMF is due for the conductor. The loop has now been rotated through half of the one alternation of 180 degrees preceding the quarter cycle is applied with the period to be shown the same with the procedure that's applied with the second half of the rotation, 180 degrees and 360. The curve appears with the shown below. The only difference with the polarity inducing the voltage, where previously polarity was positive and now negative, the sin curve shows the value of the inducing voltage each instant with the time duration rotation of the loop. Notify that the curve is 360 degrees. Two alternations represent one complete cycle of the rotation. Alright, so the 180 degrees shows one alteration, which is 180 degrees from the current conductors moving the parallel lines for the direction current of the rotation conductors currently directly across the maximum direction of the current. These show at lines A and C that has reached 180 degrees. Then in the opposite direction, the directly across the field, the EMC would be the other alternating direction from 180 to 360 degrees. Assume the closed path is provided across the ends of the cube inductor loop. You determine the direction of the current loop with the left-handed rule with the generators. Refer to figure 1-9. The left-handed rule is applied for the first place. For the left-handed illustration, within the fingers are shown the thumb with the now pointing the direction of rotation relatively movement of the wire. The magnetic field of the forefinger will point the direction of the magnetic flux north or south. Middle finger pointing out on the paper will be direction of the electron and current flow. This is other words known as the Fleming law. Rotation current with the and E with the remember with the finger point with the quantity, U with the memory with the fine cools, MY for the direction of the movement they find, F for the direction of the flux north and south, closed direction with the electron and current flow. By applying the left-handed rule with the dark half of the loop, figure 1-8, we'll find with the current flow of the direction indicated with the heavy area. Similar by using the left-hand rule on the light half of the loop, we'll find the current therein flows in the opposite direction. 2 for the voltage loop, and then add another one total EMF. The EMF will cause the current in the loop. The loop rotates the position figure shown in D, the figure 1-8. With the action reverse, dark half of the moving instead of the down, light half of the moving down instead of up, and applying with the left hand with the rule. Once again, you will see the total induced EMF, the result of the current have the reverse direction voltage to build up in the maximum new direction shown with the sin curve of the figure 1-8, and the loop to finally return to the original position E, which is the point of the voltage is again 0. The sin curve that represents the one complete cycle of the voltage generated with the rotating loop. The illustrated used in the chapter with the wire loop in the closed direction. Actual practice of the loop can be moved in clockwise or counterclockwise, regardless of the direction of the movement. The left-hand rules apply. If the loop is rotated with 360 degrees steady rate with the strength of the magnetic field is in uniform voltage with a sim wave of the voltage indicated the figure 1-9 continuous rotation with the loop will produce a series of sim wave with the voltage cycle, in other words AC voltage. As mentioned previously, the cycle consists of the two complete alterations period of time. Recently, the hertz has been indicated in one cycle per second. If the one cycle per second is 60, one cycle in a second, the 1 hertz is then 100 cycles per second equal to 100 hertz, and so on. Therefore, then throughout the Navy electronics training series, the term cycle is used with no specific time element involved. The term hertz is used when the time element is measured in seconds. When a conductor is rotated the magnetic field, what points of the cycle of the EMF at the maximum amplitude, the minimum amplitude. One cycle is how many degrees of the rotation of the conductor magnetic field. Shape the left-hand rule, you determine the direction of the current over the generator. However, the AC voltage produced as the AC generator. Frequency in a loop. The figure 1A makes one complete revolution each second. The generator produces one complete cycle of the AC during each of the 1 hertz or 100 cycles per second. Increase the number of the revolutions increase the number of the revolutions to 2 per second. Produce the 2 complete cycle of the AC or 2 hertz. The number of the complete cycle of the alternating current voltage completed each cycle, and referably as a frequency. The frequency is always measured expressed in hertz or cycles per second, 100 cycles per second. The alternating current frequency is an important term to understand since the most of the AC electrical equipment require specific frequency proper operation. Question 20 says define frequency. Period. Individual cycle of any of the sim wave represents a definite amount of the time. Notice that the figure 110 shows the 2 cycles of the sim wave, which are a frequency of 2 hertz. Since 2 cycles occur with each of the second, the cycle must require a 1/2 second or 1/2 second of time. The time required to complete 1 cycle of the waveform is called the period of the time. Figure 110 shows the period is 1/2 second. The relationship between the time and the frequency, T is time, frequency is F, indicated in the formula. T is equal to 1 over the frequency, and frequency is equal to 1 over the time, or where the T is period in seconds, and is equal to 1 over the frequency in hertz, or frequency is equal to 1 over the seconds. Figure 110 shows the period of the sim wave, the amplitude, the period of the positive alteration. Negative alteration is on the bottom, positive alteration on the time. Notice that there are 2 positive alterations when it goes from negative 1 second. There's 2 cycles in 1 second. Time and axis, a negative alteration and positive negation period. Each cycle of the sim wave shown in figure 110 consists of the 2 identical shape variations, voltage variation, which occur during the time of the voltage. Positive the alteration variation occurs during the time of the voltage. Negative is called the negative alteration sim wave. The 2 alterations identical size and shape but the opposite polarity. The distance from 0 to the maximum value of each of the alterations is called the amplitude. The amplitude of the positive alteration and amplitude of the negative information alterations are the same. Alright, wavelength. The time they take for the sim wave to complete 1 cycle to define the period of the waveform. The distance traveled in the sim wave during the period is referred to as wavelength. Wavelength is indicated with the symbol or the Greek lambda. Show the wavelength as by a signal. This distance of the waveform, 1 point with the same with the point new cycle. The next cycle, you can observe the relations examined in the figure 111. The point of the waveform measurement of the wavelength between is not important. Long distances measured in the same point of the next cycle. And figure 112 show the wavelength, positive alteration period, positive alteration, negative alteration period of time. Wavelength distance is 1 wavelength. 1 period of time contains a alternation of positive and a negative alteration. Is 1 wavelength distance or a period of time. Wavelength between wavelength measurement, wavelength at its high amplitudes are marked weighted measure. When terms are indicated in 1 complete cycle of the waveform, what is the positive alteration and what is the period of the wavelength over the sim wave measurement, respectively. Alternating current value. Discussing alternating current voltage, you will often find it necessary to express the current and voltage extremely in terms of the maximum peak values, peak-to-peak values, the effective values, the average. Effective values, average values, instantaneous values. Each of these values are different, meaning it is used to describe a different amount of the current and voltage. Peak and peak-to-peak values. Refer to figure 113. Notice that show the positive alteration sim wave half the cycle of the AC, the DC wave, and a DC waveform occurs simultaneously. Note that the DC starts and stops at the same moment it does with the positive alteration. Both the waveforms the same maximum value, however, the DC values are greater than corresponding AC values at all points except at the point where the positive alteration passes through the maximum value. At this point, the DC and AC values are equal. The point of the sin wave is referred to as the max or peak value. So you have maximum value of the DC waveform shown at 180, the maximum AC peak of the valve of the AC waveform at 90 degrees. During each one complete cycle of the AC, there are always 2 maximum peak values, and 1 positive the half cycle and the other negative half cycle. The difference between the peak positive value and the negative peak value, called the peak-to-peak value of the sim wave, the value is twice the maximum peak value. And sim wave is composed of the measurement of AC voltage. Note that the difference for the peak-to-peak and peak-to-peak values in figure 114 using alternating voltage and current effective values are using alternating voltage and current as expressed in effective values are a term usually studied later rather than peak-to-peak values. Alright, so you have your peak value, peak value, and then peak value for the negative and alteration. Each one is a different one. If you go to peak value, it's the top of the positive alteration and negative alteration in full 1/2 cycle, or in one period of the one period. It's half of the one period of cycle. This is the peak to peak value. How does it mean the peak and the peak to peak values of AC? How many times the maximum peak value of the EMF force current reach in one cycle for AC? All right, instantaneous value. Instantaneous value of the alternating voltage of the current voltage value of the voltage current of the one particular instant. The value must be zero for the particular instant with the time of the in the cycle, which for the polarity of the voltage change. It may also be as a peak, same with the peak value of the selected instant. At the time of the cycle, the voltage current stops increasing and start decreasing. There are actually infinite numbers of instantaneous value with between zero and peak value. So actually, in your instantaneous value, there are actually infinite number of instantaneous values between zero and peak value. Your average value of the alternating current instantaneous value of the of an alternating voltage current is what value of the voltage or current in one particular instant. The value may be zero in a particular instant of the time of the cycle which the polarity voltage is changing. It may also be same as the peak value is if selected if selected is the instant time cycle which if the voltage current stops increases or starting decreasing. There are actually infinite numbers of instant values between zero and the peak value. Your average value. The average value of alternating current of the voltage is the average of all of the instantaneous value of the during one alteration. Since the voltage increases to zero to the peak value of the decreases back to zero during one alteration, the average value must be sum of the value. Average value must be some value between the two limits. You can determine the average value by adding together the series of the instantaneous values of the alteration between 0 to 180 degrees, and then dividing them by the number of the instantaneous values used. The computation would show the one alteration of the sine wave as an average value equal to 0.0636 times the peak value. The formula average voltage is the voltage average is equal to 0.636 at the voltage maximum. And where the average voltage is one alteration, that voltage maximum, the peak value is similar. The formula average current is ampere average is equal to 0.63 over the amperage maximum, where amperage average is average current with the one alteration, amperage maximum is the maximum peak current. Do not confuse the above definition with the average value of the average value of the complete cycle of the because the value is positive during the one alteration, negative during the one other alteration. The average value of the voltage varies occurring during the complete cycle. Because the voltage is positive during one alteration, negative during the other, the average voltage varies values according during the complete cycle is zero. So if you have one alteration, negative, the average cycle is zero. If any of the point sine waves select with the random value of the current voltage at the measure of one particular moment of the value is measured with the value current with the voltage computed with the average owing the instantaneous during the negative alteration sine wave with the average value with the instantaneous current of the voltage during one of the complete cycle of the sine wave. What mathematical formulas are used to find the average of the current, the average value of the voltage for the sine wave? If the voltage max is 115 volts, what is the average volt? That would be average. The average is equal to 115 volts times 0.636, and average amperes of 1.273 would be the average. Divided by 0.63 would be your amp maximum. Effective value of the sine wave: the voltage max, voltage average, amp max, amperage, the average are value of the values used in AC management. Another value with effective value of the AC, the value of alternating voltage current. They will have the same effect with the resistance comparable variable. This value of the alternating value voltage and current will have the same effect with the resistance comparable to the voltage value of the direct voltage and current will have the same resistance. In earlier discussion, we are told that the current flow of the resistance heat produced when the direct current flow in resistance, the amount of electrical power converted into the heat equals amperes times the ohms, amperes squared times the ohms, watts. And however, since the alternating current have the maximum value of 1 ampere does not maintain a constant value, the alternating current will not produce as much heat in a resistance with a direct current with 1 ampere. Alright, so compare the heat effect of 1 ampere to the DC with heating effect of 1 ampere to the AC. 1 ampere has 100 degrees Celsius at 1 ampere, and AC has 70.7 degrees Celsius, with and the resistors are equal. And also, this has a I'm not sure what that symbol is. Maybe we'll get to that. Examine the view A and B with the figure 115. Note that the heat with the 70.7 degrees produced 1 ampere. The alternating current with the AC with its maximum value with the 1 ampere is known as only as 70.7% of heat of 100% at 100 degrees Celsius produced as 1 ampere direct current mathematically. The heating effect of 1 maximum AC ampere is 70.7 degrees Celsius over 100 degrees Celsius, or the heating effect of 1 maximum DC ampere is 0.707. Therefore, effective value of the 1 ampere efficiency of the 0.707 is time of the amperage max. Rate of the heat produced is the resistant form of the condition basis of the establishing the effective value of the alternating current. The heating effect method of the alternating current is said to have an effective value of 1 ampere to produce the heat of the given resistance at the same rate with it does 1 ampere of the direct current. You can compute the effective value of the sim wave of the current every area degree with the accuracy by taking the equal space to instantaneous value of the current along the curve and then extracting of the square root of the average sum of the squared value. For this reason, the effective value is often called the root mean square, or RMS value. Thus, your amperage efficiency is equal to the square root of the average sum of the squares of the ampere instantaneous. Seen another way with the effect of the root mean square of the amperage efficiency of the sine wave with the current with the 707 at time, but the maximum value of the current is thus the amperage efficiency is 707 times the amps max. With the amperage efficiency, know that you can find the ampere max by using the formula ampere max times 1.4014 is times the ampere efficiency. You might wonder where the constant 1.4014 comes from. To find out the examined figure 115, read the following explanation. Assume that DC, notice that it's 707 times, it's times 2 is 141, 1.4114. Also assume the AC figure 115B with instant increment until the temperature resistor is 100 degrees Celsius. At this point, it's found that the maximum AC value is 1.414 amperes required in order to have the same heating effect with the direct current. Therefore, in the AC current, maximum current is required at 1.414 times the effective current. It is important to you to remember above the relationship that the effective value of the amperage efficiency is of any sim wave. The current is always 707 times the maximum value of the amperes. Alright, since alternating current is called the alternating voltage ratio effective value of the voltage maximum voltage, same with the ratio effectiveness current to the maximum value of the current, the same with another effective of the root mean squared of the voltage efficiency with the sim wave voltage, or 707 times the maximum value of the voltage max. Thus, voltage efficiency of the square root of the average sum of the square of the voltage instantaneous, also, or the voltage efficiency is equal to 707 times the voltage max, or the voltage max is equal to 1.414 times the voltage efficiency. When the alternating current and voltage values specified with the book on the diagram, the value of the effective value there is definite statement of the counter. Remember, all the meters on the left of the market counter recalibrated to indicate the effective values of the current and voltage problem. The circuit known that they have the alternating voltage of 120 volts, peak, and the maximum current of 30 amperes, which is the peak voltage effective of the currents, are given the amperage. Or the max voltage is 120 volts. The amperes max is 30 amps, so the amperes max is 1.414 times the voltage efficiency. The voltage max is equal to 1.14 times 120 volts, or 169.68 volts. And then you have your voltage max, so the amperes efficiency is 0.7 times the amps max. The amps efficiency is 707 times 300 amps, or 21.21 amperes. Figure 116 shows the relationship between various values to indicate the similar amplitude. Review the figures illustrated and ensure that we understand that the values indicated. or show the various value of the indicated sim wave, the percent of the peak at 0 to 100 on the positive inductance. 707 is effective, 6.36% is the average peak to peak, and negative peak. So what is the most convenient base for the comparing alternating direct voltage current with the value of the AC with the comparison of DC with the formula with the finding effective value with the alternating current with the peak value with the sim wave with the 1000 volts effective with the ambient voltage efficiency value with if the amperes efficiency value is 4.2415, what is the amperes max? Sim waves in phase. When sim wave voltage is applied with the resistant current is also a sim wave. This element follows the law, which is stated that the current is directly proportional to applied voltage. Now examine the figure 117. Note that the sim wave with the voltage resulting in sim wave with the current is superimposed. Same time axis. Notice that all the voltage increase with the positive direction with the current with the increase with the belonging it. Then with the voltage reverse direction with the current also reverse the direction with the two sim waves such that it was represented with the figure 117 precisely step one and another are said to be in phase. These to be in phase the two sim waves must go through the maximum and minimum points at the same time in the same direction. So, for voltage and current wave, show the current wave and the voltage wave, it would be their amps over the volts. They also pass at the same interval at the time of the axis of your alternating positive and negative inductance on the sim in the wave. In some currents, some circuits with several sim waves that can be favor that each of the other. Thus, possible to have two or more voltage drop than each of other, than also favor the circuit current. Or your sim waves out of phase. The figure 118 show the voltage of the voltage E1 is which for the conservative start at 0 time. At time number 1 is voltage E1 number 1. Reach of the positive peak. The voltage E2 starts its rise in time 2. These voltage waves do not go through maximum minimum points at the same instance of the time phase difference existence between two waves. Two waves are called out of phase, and two waves, the figure 118, the phase difference of it shows. Alright, so when they're not at the time of axis, it's out of phase. So you have E1 meets it in between 90 and 108 degrees at this point, at the peak between 90 degrees in phase E1 and E2. Time 1, time 2, positive induction. To further describe the phase of the relation between the two sim waves, the term is lead and lag, or the amount in which one sim wave leads and lags another sim wave that is measured in degrees. Refer to the again with the figure 118. Observe that the wave E starts at 90 degrees later than time that does the E1. You can also describe the relationship stating that voltage E leads the wave E2 by 90. Or the wave the voltage E2 it lags where wave E1 by E1. Either statement is correct. The phase of the relation between the two sim waves is important. Remember, these are out of phase. It is possible for one sim wave to lead or lag another sim wave by a number of the degrees except 0 or 360. When the later so you have your hertz would be 6 in 1 second. Remember that. When the later condition exists, the two waves are said to be in phase. The two sim waves that different with a phase of 45 degrees are actually out of phase of each other, whereas the two sim waves that differ phase by 360 degrees are considered be in phase with each other. Phase relationship is quite common, shown in figure 119. Note that the two waves that illustrate differ in the phase 180 phase by 180. Note that although the waves pass through the maximum and minimum value at the same time, the instantaneous voltage are always the opposite polarity. If the two such waves exist across the same component, the waves are equally amplitude that cancel each other out. The different amplitudes result in wires that have same polarity. Large wave has amplitude equal to the difference between the amplitude of the two waves. So the voltage wave at 100 degrees, 108 degrees out of phase. Two different phases between the two sim waves and located at the point of the time axis where the two waves cross at the time axis traveling in the same direction. The number of degrees between the crossing points is the phase difference. The phase difference. Wave of the cross the number of degrees between the crossing points is the phase difference. The wave that crosses the axis at a later time on the right time axis is said to lag the other wave. When the voltage wave of the current wave of the circuit is considered to be in phase, when the two voltages are considered to be out phase, when the phase relations to the voltage is different than the phase of 360. How to determine the phases between two sim waves are plotted on the same graph, and also the Ohm's law in AC circuits. Alright, many AC circuits contain resistance only. The rules of the circuit are the same. The rules apply with the DC circuit. The resistor length, heating amps, elements. Example: the positive resistive elements. When an AC circuit contains only resistance, the Ohm laws, the Kirchhoff law, Ohm laws, and Kirchhoff laws, and various rules that apply to voltage, current, and power. And the DC circuit is also applied to the AC circuit. The Ohm law's formula for the AC circuit is also stated as the amperes efficiency over the volts efficiency over ohms, or once again, amp equals voltage over the ohms. Remember to note that otherwise stated, all the AC voltage and current values are given in effective values, or as effective value. The formula Ohm laws can be stated as ampere average is equal to voltage average over the ohms, or amperage max over the voltage max over the ohms, or peak to amps peak to peak is equal to voltage peak to peak over the ohms. This is important to keep in mind. Do not mix with the AC value with the sum of the effective value with all value. The formula must be effective value. When solving the effective values, all value of the formula must be effective values. Similar when you solve the average value, all values must be average values. The point shall be clearly after you work the following problem. The series circuit consists of two resistors: resistor 1 5 amps, resistor 1 5 amps, resistor 2 12 ohms, and alternating voltage sources. So for 120 degrees, 120 volts at the ampere voltage. Ampere average, Resistance is 5 ohms, resistance 2 is 12 ohms, resistor 2 is 15 ohms. And the voltage average is 120 ohms. So the reverse solve of the total resistance of the resistance total of R1 plus R2, resistor 1 plus resistor 2 is 20 ohms. And the alternating voltage is assumed with the effective value if it's non-specified, but the otherwise applying the Ohm's law. So you'd have 20 ohms over the and the amperage would be, and the volts is 120 over 20 ohms would be 6 amperes of the ampere efficiency. The problem, however, the average value of the current ampere average for the effective value of the current average voltage current that must be first determine the peak value of the maximum. The amperage max is 1.414 times the amperage efficiency, 6 amps, which gives you the amperage max at 8.484 amps. You can find that the amperage average just by substituting 814 amps over the ampere average. Or 6.63 average formula. So the average amp is 5.4 rounded off to 1 decimal place. Remember that you can Ohm law forms to solve any purely resistive AC circuit problem. Use the form in the same manner as you would in solve the DC circuit problem. The series consists of the 3 resistors: resistor 1 10 ohms, resistor 2 20 ohms, resistor 3 15 ohms. You'd have 35 ohms, and alternating voltage source of 100 volts over 55 with the effective current there's the amperage average. So once again, you'd have the amperage. So they take 6 amps times 1.414 maximum to get the amperage max, and then the average times 0.63 would give you your amperage average. And the voltage efficiency of 130 volts, and the amperage efficiency is 3 amps. What is the total resistance of the resistors? T is total. I won't do that one. Moving on to summary of the chapter 1. New tape.